Bye, Becca.
Bye.
So let's talk. I guess the goal here is what we're going to do is double integrals in polar coordinates. I know. No, we're gonna do doubles in rectangular and in polar, and then we'll do triples.
That's shady because you asked us which one we wanted to do first.
I'm pretty sure we said triple.
Oh well.
We definitely did, but it's okay. Because now we're doing this.
No.
Um,
It's not okay.
You just gotta deal with it.
So I guess maybe we should review polar just slightly. So if you think about polar world.
Like spherical or?
No, it's just polar. Polar. But I guess if we meant polar is technically cylinder. Right?
So curves in polar coordinates are when you have r equals f of theta, and theta is the angle in standard position, and r is the distance from the pole or the origin, right? So as you see, as we increase theta, this r is changing, right? Do you guys see that?
Yeah.
And then the conversion back and forth between Cartesian or rectangular and polar is x equals r cosine theta, y equals r sine theta, and x squared plus y squared equals r squared. And then theta is the inverse tangent of y over x. Okay, those are the sort of governing equations for this business. So what we're gonna yay. My markers all are like the caps. Something's weird with these. When you take the caps off, that like the whole marker comes apart. So let's take a look. Just a motivating example of what's happening here. Let's say that we want to integrate this function. Actually, no, let's just do the. So let's say we want to integrate that function over that area. Follow what I'm saying? Mm-hmm. So hopefully you see that integral is not going to be pretty. Okay, first of all, like if we're going to do this as a, integrate with respect to x first or y first, we still are going to have to break this up into two chunks. Because, if we go x first or y first, either way, we're hitting the same curve twice. So we're going to have to break it up. This curve is not real friendly because there's going to be a nice fat radical involved, right? So this is the kind of example that might motivate us to switch coordinate systems. Okay? So in Cartesian coordinates or rectangular coordinates, dA, what is dA? What does that mean over here? What is dA of this? Well, just dA by itself is just a little chunk of the area of this, right? And when we do in rectangular or Cartesian, dA is equal to dx dy or dy dx, correct? But if we convert this to polar, oh, I forgot about you. You're done?
Yeah.
Holy smokes. If we convert this to polar, it's not quite as simple, okay? So that's what we're going to do, is we're going to convert this to polar. Now this part's easy to convert to polar.
We have a question.
Yeah.
I'm gonna do this. Are triple integrals in spherical coordinates?
Yes.
No.
That's really annoying.
It's easy to convert what I just put inside the bubble.
R.
Like that, it's easy to convert that to polar. What is it?
R.
Square root of r squared, which is just r, right? But now, this right here is not quite so simple. Because if you think about over here, in rectangular coordinates, where did dx dy come from? Well, if you think back, we took the region and we partitioned it, right?
Oh.
And it was really like the area of a little rectangle that was delta x by delta y. And then we made those infinitely small, and it's dx dy or dy dx, right?
So, oh my gosh, that makes so much sense.
But in polar, dA is not just going to equal dr d theta.
Because r times theta is in the area.
Because dr times d theta is not the area. So that's what we got to figure out.
Is it just dr? Because it's all the like infinite radius. I mean,
Oh!
Because-
If it's a circle, that makes sense.
no, even if it's not, because it's all the different. Because I remember when we did whatever the flower shapes are, it's all of the infinite radii like added up together
From
So
the origin.
from the origin. So is it still that?
Kind of. But
But if you think about it, that would overlap. Like, think about having a bunch of lines this way. There would be gaps once you get farther away.
Okay.
so let's look at this. Okay. I mean, we're going to tie all this together from last year. I mean, the two variables involved in polar coordinates are what? R and theta. Okay. So if I think about, I'm going to take just a little sub chunk of this. Okay.
So if double integrals are polar world and triple integrals are spherical world, then cylindrical coordinates kind of seem pointless.
Cylindrical are also triple. Because cylindrical is just polar with a z coordinate.
What do you understand?
Yeah.
So it's different?
I mean, it's
Or is it like a
cylindrical is polar. It's just you have z involved as well.
Okay.
Okay? So what I'm going to do is I'm going to consider this as a chunk. Like I'm going to look at this thing right here, okay, as a polar rectangle. It's going to be the equivalent of this right here. Okay? So
Oh, arc
So this right here, that difference right there is a change in theta. Okay? This distance right here is a change in r. Like that's an r value and that's an r, and this is an r value, right? So the difference of those is a change in r.
So is that two polar rectangles?
Okay? No, this is the one we're talking about right here. Okay? So we could say that the area of this rectangle is this length right here, which for right now I'm just going to call L, times this length right here, which I'm going to call, I already have called, delta R. Okay? But what is L exactly? Well, L is actually an arc length. Okay? L is an arc length. And if you remember, maybe you've forgotten, the length of an arc with an angle swept out of theta is actually equal R times the angle. Okay? So if this right here is an R value, and this right here is the theta angle value, what does L actually equal? It's R delta theta. Because theta, I mean this angle right here. What's that?
Would that be just for a circle then?
No, it's any chunk of polar area. So now over here, the area of this rectangle I'm going to say is R delta theta delta R. And then I'm going to rewrite that as R delta theta. Okay. And then, of course, what happens if we, make delta theta approach 0 and delta R approach 0? What is this going to become? R, what's that going to become is dr. And what's that going to become as that approaches 0? D theta. Okay? So a piece of area, like if I'm going to call that delta A, this right here, after you make delta theta and delta R go to 0, like we kind of do in theory, this becomes dA. So dA in polar coordinates, the infinitely small piece of area that you're going to add, take each one of the values and multiply it by, and then add up, dA actually equals R dr d theta. Okay? So now over here, if I was going to change this problem into polar coordinates, dA is going to get replaced with R dr d theta. Okay?
So it's R dr.
R squared, R.
Yeah, in this particular example, you're exactly right, Wally. It's going to be R times R dr d theta, or R squared dr d theta. Now, we can go ahead and put bounds on this. Okay? If I look at this picture right here, what are the bounds for R in this particular picture?
3.
0 to 3. And what are the bounds for theta that are going to give you that entire picture? 0 to 2 pi. Okay? So the key to this is understanding that dA is actually not, it's not a one-to-one trade. Like dA in Cartesian is dx dy. But when I convert that, there's like this, it's not a one-to-one conversion. When I make that change of variable, dx dy becomes R dr d theta. Okay? Or dy dx becomes R dr d theta. Those two quantities are that infinitely small piece of area. Yeah.
So does this mean we just multiply everything by R when we're changing from dA to dr d theta?
It means that when you change from dA to dr d theta, you always put in that R.
But if it's already dr d theta, like if the problem already has it set up like that,
Yeah, then you wouldn't.
okay.
It's only when you convert.
Okay.
Yeah. Now, if you remember last year, Okay? If you remember last year when we were finding the area of those polar regions, there was a formula that we learned to find that area. It was 1/2 r squared d theta. Remember that?
Yeah.
So if you go back and think about that formula for a second, let's say, I'm not going to finish this problem now. Okay, I'm going to quit and start something else here. Because I want to dig into this RD theta bit a little bit more. Let's say I have a polar curve, like one of those flowers. Okay? So let's say I have a polar curve, and I want to find, this is some polar curve, r equals f of theta, and I want to figure out the area of that leaf, right? And maybe theta 1 and theta 2 are the two theta values that will start and stop that leaf. If we were to do that problem last year in Calc 2, it would have been this. You would have said, oh, I know how to do that. It's the integral from theta 1 to theta 2 of 1/2 r squared d theta. And then you would have just taken that equation and substituted it.
Is that taking, that's doing the double integral, but already.
So
Oh, that's weird.
if I think about this as a double integral and just say, okay, I want to find the area of this. If I want to find the area of this, I'm going to integrate dA. So I'm going to replace dA with r dr d theta, right? And what's r going to go from? Well, r is going to go from 0 up to f of theta. What's theta going to go from? Theta 1 to theta 2, right? And then when I integrate this, I get theta 1 to theta 2, 1/2 r squared, evaluated from 0 to f of theta. Guess what? It's exactly what we had over there. Okay? Now, when we did this last year, we developed this formula a totally different way. Well, not quite a totally different way, but kind of a different way. We didn't involve, like, we weren't looking at dA. Okay? The way we looked at it here. Arc length was still involved, though. Okay?
I think there's the first teacher to like make you derive an equation and then give it to you.
So the key thing that we have to remember when we're talking about polar integrals and double integrals of polar coordinates, is that dA is r dr d theta. Okay? You have that extra r involved. Okay? And in fact, that extra r is something called the Jacobian. Yes. If you go back to that problem that you had as a problem set, the Jacobian matrix, the Jacobian is sort of that, like, what do I want to call it? It's that factor. It's the thing that tells you how to get from dA and dx dy to dA in some other coordinate system. It's the exchange rate, basically. It's like, well, in Cartesian, it's dx dy, but I need some other factor here to convert dx dy into dr d theta. There's something I got to do to it so that it's a one-to-one transfer. Okay? When we convert to cylindrical, and when we convert to spherical, there's also a Jacobian that we'll derive the same way. Okay? Okay, so let's do some problems. So the first question really is, why would you want to convert a double integral to polar coordinates? Okay, because it makes it much simpler to compute. That first example that we just did in Cartesian would have sucked, but in polar, it's easy. I mean, I can integrate r squared, right? And then the bounds for r and theta were both constants. Yeah, that's easy. So when you have an integral in Cartesian coordinates that involves anything circular, it's screaming polar. So if your region is circular, you want to think polar, or if your function is circular, you might want to think polar. Okay? So let's do this. First, set me up a double integral in polar coordinates that will give me the area of this right there. Set me up a double integral in polar coordinates that is going to give me that area. Now, a good chunk of this problem is essentially the math that you did last year, because you still got to figure out the bounds and all that. Keep getting swung out.
Do we want to? We don't want to do it for the full circle. Just that chunk, right?
Just that chunk.
There goes here.
So that should be your integrand. Now, what are your bounds for R?
For R, 4 to 9.
2 to 3.
2. Theta 0 to pi over 2.
Exactly.
Oh, I got confused because when you're given two functions, but they're not the functions that you're integrating, they're just functions.
That's just making up the bound or the region. Right.
That's what I
Okay. Those two equations were just making up the region. Now I could change this problem and be like, well, if you know how to do that, then I could say, all right, well, do this. I don't know. How about x squared times y dA? Now do that problem. Same region. Set it up. No.
Oh, because you have to convert.
Now I've got a function here, not just dA. This right here is just integrating dA, and you're adding up dA and getting the area. Now I'm integrating a function over that area. But the bounds are still the same. And dA is still the same. The difference is x squared times y. Right, I got to convert this to polar. So that's r squared cosine squared times cosine times r sine theta. So this piece right here, that's the x squared times y. That piece right there is the dA. So what does that end up being? R to the fourth? So that's r to the fifth over 5, evaluated from 2 to 3. So 3 to the 5th over 5 minus 2 to the 5th over 5. Right? Yeah. That's 3 to the 5th minus 2 to the 5th over 5. So I'm going to pull that out. And now I've got to integrate from 0 to pi over 2 of cosine squared theta sine theta d theta.
Yeah, that's a hard one.
No, that's actually a really easy one.
Is that one of those like trig subs that we're supposed to know?
That's not a trig sub.
It's a u sub.
Not trig sub. Oh, that's a u sub.
U is cosine theta.
Oh,
Du is negative sine. Right?
That makes sense.
So this is negative 3 to the 5th minus 2 to the 5th over 5 times the integral of u squared du. You want to change the bounds or just write it as negative 3 to the 5th minus 2 to the 5th over 5. That's u cubed over 3. So that's cosine cubed theta over 3. Evaluate from 0 to pi over 2.
wouldn't du be negative sine theta d theta?
Yeah, that's just laziness.
I'm just rusty on the u sub.
So this is negative 3 to the 5th minus 2 to the 5th over 5 times cosine cubed pi over 2 over 3 minus cosine cubed of 0 over 3. That's 0. That's 1. So this is negative 1. So this ends up being 3 to the 5th minus 2 to the 5th over 5. What do you think about that?
Not too bad. I mean, again, the worst part's just forgetting how to do analytic
Well,
differentials. As always, it's the worst part.
Calculus is easy. It's the algebra that sucks.
Yeah. That's what I told like everyone. They haven't believed me.
Let's try another problem. Okay.
this. Oh, because the functions.
I just noticed that our textbook uses D instead of R.
They use diameter instead of radius?
No, it's for region,
Oh,
for the region.
yeah, hang on.
Okay, so see if you can set that up. In fact, well, I'd say it's 6 1/2 dozen the other, whether you would want to convert this or not, because the square root of x squared plus y squared is actually not terrible to anti-differentiate. Now I could make it really difficult to anti-differentiate if I just stuck it over x, or if I stuck it even over x squared. So let's just pretend it is difficult. The hard part about this is converting the region to polar, and that's why I chose it.
So would you just have to say r cosine theta equals 1, r cosine theta equals 4.
Okay, so let's do the integrand first. What do you want to do that? So that's r,
R squared.
and then r dr d theta. Okay. And now, Joe, you're saying what?
So we just have to say that, yeah, and then solve for r. But then we wouldn't have numbers.
So r is 1 over cosine theta, right?
But not for the first two.
Well, r is going to equal 1 over cosine theta, right?
I was thinking that the
Yeah.
inside ones have to be numbers, but it doesn't.
So that's secant theta. And this would be r equals
4.
4 over cosine, or 4 secant theta. Right? So could we say that r is going from secant theta to 4 secant theta? And what's theta going to go from?
0 to pi over something. What's 45 degrees in polar? I mean, radial. Pi over 4. The math.
Okay, that makes sense.
Okay.
Is that it?
So that's set up. Now could you finish it?
Right.
So that's r cubed over 3.
No. What's the degree?
This one. Yep. Yep.
And then minus.
So this ends up being this. 0 to pi over 4 of 63 over 3 secant cubed theta d theta. Right?
Sure.
Because that's 64 thirds minus 1/3. Yeah? So that's 63 over a third.
That's 21. Wait. Yeah.
Yeah, good call. So 21 secant cubed theta d theta. Now I just happen to have memorized the antiderivative of secant cubed because we did it in class in Calc 2 days ago. So I'm going to tell you. It's 1/2 secant theta tangent theta minus 1/2 natural log secant theta plus tangent theta.
I remember that. We were just talking about that. Sectan. You remember sectan? That was just my class? Oh.
So that's 21 times 1/2 secant of pi over 4 is actually radical 2. Tangent of pi over 4 is 1. Now let's do 0. The bottom limit, when I plug 0 into this, tangent of 0 is 0. And secant of 0 is 1. So that's 0. Tangent of 0, secant of 0 is 1. Natural log of 1 is 0. So the whole bottom bound disappears. So there's the answer to that. Or you want to say, what, 21 halves times radical 2 minus natural log of radical 2 plus 1. Oh, I mean, it's not hard if you remember how, stuff from last year, for sure. Makes it easier. Okay, so what I'm going to have you do is in 5.3, I'm going to have you do 128 to 132, but I'm changing the directions on those. What I want you to do for those is set up a double integral to find the area. Don't compute it, just set it up. Okay? They give you these regions, and I just want you to set up the double integrals to find the area. That's going to help you setting up the bounds on future problems. Okay? Then I want you to do 135 to 141 odd. And then I want you to do 148 to 151. Set up only. Just convert them. Don't compute them. Does that make sense?
Yep.
Until Thursday.
Yeah, that's good for now, I think.
That'll do for the next week.
I don't know. Hopefully, I don't know what to think. There's part of me that's like, yay, hooray, hippie. But then other parts of me are like, no, it's terrible.
See, now that everyone's talking about it so much.
Yeah, I hope you're having fun skiing.
Our teacher predicted